Hey everyone, welcome to week one's lecture. Today's lecture will be covering sound and how it's created, how it moves, and a little bit about how our auditory system processes it. We'll start with what has been called the dumbest philosophical question in the history of philosophical questions. If a tree falls in the forest and nothing is around to hear it, does it make a sound? I'll give you a second to answer that in your head. No doubt many of you answered yes, but the answer is not that simple. So, sound is a vibration that propagates as a typically audible mechanical wave of pressure and displacement through a medium such as air or water. And these waves are made up of two different parts. Compression, which is an area of high pressure that forces particles of a medium closer together, and a rarefaction, which is an area of decreased pressure that forces particles of a medium further apart. While the falling tree does create vibrational energy that displaces molecules, transferring that energy through the air, there's a little more to the story. The key part of this question is, and nothing is around to hear it. In both physiology and psychology, sound specifically is the reception of these mechanical waves and the perception by the brain. Now, right around you, all around you, there are pressure waves moving through the room or space that you're sitting in that will never be sound to you. That's because your ears are not designed to hear pressure waves below 20 hertz and above 20K. And any pressure waves that occupy below 20 hertz or above 20K are not going to be perceived as sound to you. So this leads us to a brief overview of the ear. Our ability to hear is probably our most amazing sense for a variety of reasons, mostly for our ability to get an accurate assessment of everything auditory in our vicinity, including everything that may be behind you. Our sense of vision is powerful, but limited in that we can only really see from our center of vision out to our periphery. Our sense of smell comes close. For instance, if someone were to pass gas close by, even if they were behind you, you'd still be able to smell it. Fortunately for most of us, a person would still not be able to localize where that smell was coming from, rendering blaming it on the dog kind of a moot point. So, the ear is broken up into three parts. The first of these is the outer ear. As pressure waves hit our heads, the pinna gathers them and directs them into an opening called the concha. Then, um, then they travel down the auditory canal until they get to the tympanic membrane, which is also known as the eardrum. The tympanic membrane vibrates in response to these pressure waves. The membrane is so sensitive that it will respond to the tiniest vibration. Attached to the back of it is a tiny bone called the malleus. Whenever the eardrum moves, the malleus has to move as well, transferring that energy onto two more bones called the incus and the stapes. And the three of these bones together are called the ossicles. They're located in the middle ear. They're the smallest and most fragile bones in the human body. But in this case, small is a valuable asset to have because the smaller something is, the less energy is required to get that thing to move. So these things being very small also means they're very efficient. Um, a fourth part can be found here, and that's called the eustachian tube. Its primary purpose is to equalize pressure. If there's too much pressure on either side of the eardrum, it can't move efficiently and may end up causing damage. For instance, if you're traveling in an airplane, you want to be careful about blowing air into your ear. So holding your nose and blowing actually forces air into the eustachian tube. So you need to know whether you should be doing that taking off or coming down. And the answer is the only time you should ever hold your nose and blow is when you're descending or landing. Also, this is something you might do if you were diving because the pressure on the outside of your ear starts increasing. You need to increase the pressure on the inside of your eardrum. So just keep that in mind when you're flying next. At this point, the vibrations move from air to the fluid of the inner ear, also known as the bony labyrinth. It's comprised of three sections: the semicircular canals, which are our primary means of balance, the vestibule, which is like the entryway to the ear, and the cochlea, which is our sound analyzing organ. So the basics state that the vibration of the basilar membrane is responsible for us being able to hear. But it goes much deeper than that. The basilar membrane is in the cochlea, and it's set into motion by pressure patterns that enter your cochlea. And different parts of the basilar membrane are responsive to different frequencies. The base of the membrane is thicker and more rigid, and it will respond to higher frequencies. And the apex or end of the basilar membrane is thicker, less rigid, and responds to lower frequencies. Every object in existence has at least one mode of vibration, or at least one um, frequency that it will respond to by vibrating. And depending on the material that the object is made up of, the thickness, the flexibility, these are all things that change the frequency at which it will vibrate. And the basilar membrane's um, thickness and rigidity changes as you move along it. So, for instance, here we see a cross section of the basilar membrane and what it might look like if we were listening to a 3K tone. So as that 3K tone travels into our cochlea, the basilar membrane will be unaffected until the tone gets to the section of basilar membrane that responds to 3K and 3K alone, at which point it'll start vibrating up and down 3,000 times per second. So this brings us to the response of the auditory system. We'll start with something called equal loudness contours, which demonstrate the nonlinear function of the auditory system with regards to amplitude and frequency. Basically, what this means is that we're not equally sensitive to all frequencies between 20 Hz and 20K. Amplitude has something to say about that as well. The Fletcher-Munson curves were created in Bell Labs in 1933, and they demonstrate the nonlinearity of our ears, or in other words, that we don't hear all frequencies equally. Here we see 1K as being our reference. So if we follow this line up to the left, and we were to listen to 100 Hz and 1K together at the same time, we would have to turn up 100 Hz about 38 dB before they would sound as if they were equal in amplitude. In 1956, two scientists named Robinson and Dadson decided to update these curves. Now, our auditory system did not improve between 1933 and 1956, but what did improve was our knowledge of the auditory system and the sensitivity of the equipment that was being used to test the subjects. So here we have some loudness examples that I'd like to do with you. We have 50 Hz, 1K, 8K, and 12K. I'm going to play these for you one at a time, and I want you to pay attention to how loud each one seems to you. Bear in mind that these are all played at the exact same amplitude. So here's 50 Hz, 1K, 8K, and 12K. Now, even though all of these are played at the exact same amplitude, 1K should have sounded louder than the other three. Now, 8K and 12K, while piercing, sounded like they were lower in amplitude than 1K. Now, we could apply this in a working environment. Let's say we're mixing in a studio. It's important to remember that the most even curve for human hearing lies between 85 and 90 dB, meaning that we're going to get the most accurate listening when we listen to music between 85 and 90 dB. It's important to try and stay as close to 85 as you can. At 85 dB, you can actually be exposed to that amplitude for 16 hours straight before suffering permanent hearing damage. At 90 dB SPL, however, you can only be exposed to that for about 8 hours before suffering permanent hearing damage. So the chances of you working in a studio for 8 hours are pretty good. The chances of you working in a studio for 16 hours, probably not going to happen that often, no matter what they try to tell you. I mean, it'll happen, but you can't maintain that. So the threshold of pain is something that happens when we get into pressure levels that are significantly higher than 90 dB. Um, And at around 120 dB SPL, we start to experience tickling in the ear canal, as if someone was in there with a tiny feather moving it around. At a certain point, people will start experiencing pain as the amplitude increases, and that will increase as the pressure levels increase. This is going to be dependent on the frequency you're listening to, and it will also be dependent on the individual sensitivity of the listener. For instance, if you were listening to, I don't know, 100 hertz at 120 dB, it would be significantly less painful than listening to 1K at 120 dB. So let's move on to frequency and pitch. And oftentimes these two things are used interchangeably. However, we can start differentiating between the two in the following ways. When we're talking about frequencies, we're talking about individual components of sound that are measurable. They don't change with amplitude. And in other words, if we were listening to 500 hertz and you increase the amplitude of 500 hertz, you're still listening to 500 hertz. And when we're talking about frequencies, we're not talking about harmonic content necessarily. We're talking about the individual components of sound. Pitch, on the other hand, can be a bit more subjective. When we hear a note being played on a piano or a violin or cello, everybody's going to hear those notes slightly differently because we all have individual sensitivities to certain frequencies. The pitch can change with amplitude, and if you increase the amplitude of a note or a series of notes high enough, you can actually increase our perception of pitch and perception of the fundamental and the harmonics. It's necessary for us to be able to get a reference for the pitch that we're listening to. So while we're on the subject of frequency, let's talk ranges. Many times over your tenure here at Full Sail, um, you're going to hear people talking about low frequencies, low mids, and high frequencies without much of an explanation as to what these frequency ranges are comprised of. So what I've done is taken white noise and I've isolated specific ranges of frequencies so that you can get an idea of what low frequency sounds like, what low mid sounds like, high mids, and high frequencies. So we'll start with low frequencies. This range is generally from 20 hertz to 200 hertz. Here's what low mids sound like. Here's high mids. And lastly, high frequencies. It would be good practice to start trying to recognize these frequency ranges and common everyday sounds. You could start by rolling the window down in your car ride home and trying to isolate the low frequencies in the wind as it rushes through the window. Try with the low mids and high mids and the highs. You'll start being able to pick out these frequency ranges easier and easier as you practice doing something like this. One tool that we can use to, one, manipulate frequencies, and two, get used to manipulating certain frequency ranges, is an EQ, which is designed to alter the frequency response characteristics of an audio signal. In any given production, we can use EQs for three things: remove problem frequencies, boost complementary frequencies, or create an effect like a telephone effect. So some equalizer types: shelving, high and low, semi-parametric, full parametric, graphic, one band, three band, multi-band. We also have different types of techniques. We have additive and subtractive, for instance. Now, out of those two, which do you think is preferable? And a lot of people will use additive. And they use additive because they find complementary frequencies within an instrument and they boost them, making those frequencies louder. The problem with that is you have so many different frequencies in your mix or production vying for attention that boosting a frequency or a set of frequencies on one instrument may end up masking those frequencies on another instrument. So what I typically like to do is I will take a EQ and I will boost the frequency with a narrow bandwidth, and I'll sweep back and forth until I find a problem frequency. And when I find that problem frequency, I'll take it out. By reducing frequencies on instruments that don't need them, you make more room in your mix for frequencies to come through that need to come through. So the general parameters that you'll find on any given EQ are frequency, gain, and Q. And this is what a channel EQ would look like in Logic. Now we can use this channel EQ to create some effects. For instance, EQing a female vocal, for instance.
It has become appallingly obvious that
Or to create a telephone effect.
insanity is doing the same thing over and over.
We could use it to EQ male vocals.
It has becoming appallingly obvious that our
And once again, a telephone effect.
insanity is doing the same thing over and over.
So the reason that you want to get better at identifying the different frequency ranges and why I talked about them earlier is because if you're ever working with an engineer or producer and they ask you to adjust something in the low mids, you'll know the approximate range that they're talking about so you don't look foolish in the process. One of the things that you might end up having to adjust are effects processors called filters. And filters are designed, and devices basically designed to um, separate signal content based on frequency ranges. And what they do is remove specific frequency ranges from whatever signal you're working on, and they come in different forms. One of the hardest things to get right when you're working on a production like a mix is to achieve clarity. And this is because there's so many, like I said, there's so many different frequencies in that production that are vying for attention. And filters are a very powerful way to kind of remove frequencies that just aren't needed and are just muddying up your mix or getting in the way. So a high pass filter is one of those tools you can use to make this happen. For in every signal that you ever work with, there's going to be a fundamental frequency. It's that reference point and the harmonics above it that are important. So any harmonic that um, falls below that reference point or below that fundamental frequency needs to be removed because they're just getting in the way. Think, um, for instance, think hi-hats, right? If we want clarity in our hi-hat tracks on a drum set, we can use a high-pass filter to keep all of our hi-hat sounds while filtering out all the lower frequency drum sounds that are filtering through or bleeding through onto the overheads. So this is an example of a high-pass filter, filtering everything below the fundamental while allowing everything above the fundamental to pass through. I've got a few different examples in here so we can see what a high-pass filter does to noise, what it does to music, and what it can do to speech. So we'll get started. This first example is a high-pass filter with white noise, and we've automated the cutoff frequency so you can hear it hear as it sweeps through the range. So one by one, what we heard was the lows drop out, then the low mids, then the high mids, and so all we were left with was basically the high frequencies. Here we'll do the same example, but with music. And lastly, we'll do the same frequency sweep, but on speech.
It has become appallingly obvious that our technology has exceeded our humanity. It has become appallingly obvious that our technology has exceeded our humanity.
Next, I want to talk to you about bandpass filtering. So bandpass filtering is used to achieve something called the telephone effect. If you've ever listened to a signal on a telephone or a signal through a TV, there are going to be discrepancies that happen because of the quality of the speakers that are in use. Generally, we're going to lose a lot in the lows and some in the low mids. We're going to lose some information in the highs and high mids. If we ever want to replicate that effect, we can use something called a bandpass filter to make that happen. With a bandpass filter, you set the center frequency, you set the bandwidth, how wide you want it, and then it rolls off those frequencies above and below the filter. So we're going to do the same example. We're going to automate the bandpass filter to sweep through white noise, then through music, and see what it does to speech at the end. So we'll get started. Here's the bandpass filter on white noise. Here's that same example on music. And lastly, here's the bandpass filter on speech.
We cannot solve our problems with the same thinking we used when we created them. We cannot solve our problems with the same thinking we used when we created them.
Finally, I'm going to do those same examples, but with a low-pass filter. And low-pass filtration isn't used as much as high-pass filtration, but it does have some advantages that you can use in your production. For instance, if you wanted to get rid of noise in your kick drum, for instance, you have your kick drum that's recorded with a microphone, but a microphone does what a microphone does, and it picks up all of the other sounds that might be around it, including the snare and the hi-hats and the overheads. And so what you can do is use a low-pass filter to isolate the low frequencies within the kick drum itself and filter out all the frequencies above that kick drum. This needs to be used carefully because it's surprising how high harmonic content can go. For instance, a trombone, which is generally a bright but low frequency instrument, can have harmonics that go all the way up to 17 or 18K. So you want to be careful what you use a low-pass filter on because we don't want to cut off any harmonics that, that are necessary in the instrument. So let's hear what a low-pass filter sounds like on white noise. So in that example, we heard the highs drop out first, the high mids, then the low mids, and then the low frequencies. Next, we'll do that same example with the low-pass filter on music. And next, we'll do that same example with a low-pass filter on speech.
Only two things are infinite: the universe and human stupidity, and I'm not sure about the former. Only two things are infinite: the universe and human stupidity, and I'm not sure about the former.
And with that, we wrap up lecture 1. I hope you enjoyed it. Hope you learned something. If you have any questions about this week's assignments, please feel free to reach out to me at brianh@fullsail.com, and I'll get back to you as soon as I can. So enjoy the rest of your weekend, guys. We'll talk next week. Bye.